Classical physics describes a universe built on a smooth, continuous fabric. Quantum mechanics requires a reality built from discrete points. Reconciling these models requires an entirely different approach to the geometry of space. Observable, continuous spacetime might not be the foundational layer of reality. The continuous geometry we measure can instead be modeled as an emergent macroscopic rendering of a discrete underlying network. The Phoenix Coherence-Geometrodynamic synthesis, or CGD, is a framework constructed to mathematically bridge these discrete and continuous states. This architecture does not discard classical mechanics. It treats continuous physical laws strictly as the effective macroscopic limit of a primitive computational transport system operating underneath. To understand the origin of physical limits, we must bypass the illusion of smooth continuous space and analyze the thermodynamic rules governing this underlying network data. The CGD framework organizes reality into distinct ascending epistemological layers, building up from discrete math to macroscopic physics. This flowchart details the transport stack architecture. The absolute base is level 0, the discrete graph geometry. Moving up through levels 1, 2, and 3, thermodynamic control laws dictate stability. Finally, at level 4, stabilized network activity renders as effective spacetime geometry. By climbing this exact stack, we can trace how microscopic lattice rules dictate macroscopic physics, ultimately deriving a strict mathematical limit to the universe's informational bandwidth. The derivation begins at level 0 with a minimal isotropic planar transport graph. This is a flat network of interconnected nodes with no directional bias. The framework defines this base layer specifically as a degree 6 hexagonal configuration, known mathematically as the A2 root lattice. Under a quadratic energy functional, a degree 6 structure minimizes anisotropic transport bias while maintaining maximal packing efficiency. Large-scale natural transport systems frequently self-organize into degree 6 structures when placed under rotational and diffusive constraints. The massive atmospheric storm system at Saturn's North Pole operates as a macroscopic analog for this dynamic. Under continuous rotational stress, the flow of gas stabilizes into a precise hexagon. This planetary structure is a plausibility analog, not a direct proof of the quantum substrate. However, it demonstrates why degree 6 transport emerges as a stable pattern under constrained flow. At the microscopic scale, the hexagonal lattice provides the necessary mathematical foundation to prevent structural collapse in a highly active discrete network. The stability of this network is governed by the Genesis ordinary differential equation, or Genesis ODE. This is the foundational dynamical law dictating the persistence of the structure. The equation relies on coherence density, defined as variable c. This is the principal order parameter that determines if the network maintains its geometric integrity or degrades into random thermodynamic noise. The restorative term in the equation acts as a reaction diffusion control law. It continuously pushes back against natural entropic drift, forcing the system to maintain ordered dynamics. This simulation shows the Genesis ODE lattice evolution. On the left, the system begins from a baseline state of random thermodynamic noise. The discrete graph Laplacian operator forces adjacent nodes to share data, smoothing local variations and driving the chaotic system toward global stability. This heat map illustrates the final result. The equation drives the coherence density toward a stabilized limit known as the solvency floor, calculated at roughly 0.87093. Without this constant reaction diffusion mechanism pushing the network above the solvency floor, the discrete geometry would break down, severing the physical capacity to render macroscopic physics. To understand how information moves through this stabilized grid, we must shift our analytical frame from real physical space to reciprocal space, a mathematical domain where coordinates represent frequencies rather than physical positions. This reciprocal space plot displays the graph Laplacian's eigenvalue spectrum. By solving for the natural propagation modes of the system, a strictly bounded hexagonal structure appears in the dispersion relation. This histogram graphs the eigenvalue distribution. The uniform zero eigenvalue mode on the far left corresponds to global coherence, while the higher discrete values represent independent transport modes through the network. This maps the spectrum within the hexagonal Brillouin zone. Dashed lines reveal a strict six-fold rotational symmetry, partitioning the spectrum into 6 60-degree sectors. This symmetry organizes chaotic diffusion into discrete angular transport channels. An observational projection spanning 2 sectors creates a 120-degree rendering window. This 6-fold spectral partition acts as the primary mathematical constraint on the network. It strictly limits how many independent signals can propagate through the base geometry. We can calculate the exact number of allowable signals by applying a mathematical constraint called the chamber state closure condition to this partition space. This diagram outlines the bandwidth construction. 6 principal transport directions multiplied by 4 phase states gives a 24-state phase shell. Multiplying by 6 axes yields 144 transport channels. Quotienting out 7 structural redundancies leaves exactly 137 independent physical modes of excitation. This calculated 137-mode limit is numerically proximal to the inverse fine structure constant in quantum mechanics, which sits at approximately 137.036. Within the CGD framework, this number is the absolute dimensionality limit. It is the hard computational bandwidth ceiling for any stable, symmetry-reduced hexagonal universe. The final architectural requirement is translating this 137-mode discrete thermodynamic system into the continuous spatial curvature predicted by general relativity. This transition is accomplished through the Anoroc master equation, a modified tensor relation that scales the microscopic substrate into an effective macroscopic field. The equation modifies the classical Einstein field equations by introducing a specific substrate stress term, directly accounting for the underlying discrete transport dynamics. This additional term operates as a field-theoretic ansatz, a mathematically structured bridge, linking the localized thermodynamic coherence of the lattice to the wide-scale curvature of spacetime. Through this mathematical bridge, macroscopic gravity operates as the physical rendering of the underlying 137-mode discrete transport network, reacting to thermodynamic stress. The CGD architecture establishes a strict epistemological firewall. It isolates the empirically simulable discrete dynamics from the theoretical bridges that interpret them. The model explicitly defines its boundaries. It does not claim to execute a direct, complete derivation of the fine structure constant from pure mathematical abstraction, nor does it override established continuum physics. Instead, it models spacetime precisely as an active computational rendering rather than a passive empty void. A base relational geometry organizes into a minimal degree 6 hexagonal configuration. A reaction-diffusion equation keeps that geometry solvent. The resulting structural symmetries restrict the system to exactly 137 independent propagation channels, generating the discrete foundation that scales into observable macroscopic curvature. Reality, at its most fundamental level, may simply be the continuous macroscopic projection of a discrete mathematical network expending energy to keep itself solvent.